Yes, sir. So, yes.
Yes, ma'am. You can go ahead. Thank you.
Thank you, sir. Okay. I hope my screen is visible. Good afternoon, everyone. Thanks for joining today.
Yes,
And
ma'am.
yes, yes. So, yesterday we covered a few leftover parts of the like quantum mechanics, primarily the super dense coding that was a postulate, as well as we covered the Schrodinger equation, Heisenberg uncertainty, followed by the Hamiltonian and how the time evolution of some quantum states happen over different time, or how the quantum space, there we have seen the Laplacian operator or the gradient operator, and all those stuff we have seen. And we ended with an example that showed that how genuinely from a Hamiltonian operator we can calculate the time evolution operator, which was our unitary operator, and we can continue with that. And at the end we have seen that how from the projection operator we can which is a kind of, with respect to a particular probability, what is the projection or the probabilistic amplitude of getting that particular quantum state over the wave function at any instance of time, say t. We have seen that, and by just doing a simple modular square of that, we have seen that how to get the probability. So that was kind of what we covered yesterday. So today we will be covering completely a different part. It's completely a part of the classical ones as per our schedule. So it's a computational complexity where I've thought of to cover almost everything that you should be knowing. Today we will be covering the classical thing, and tomorrow we will be covering the quantum computational complexity classes. That is kind of the what you can see in the syllabus. Okay. So for that, those who are from computer science, it will be might be a few parts, might be you already know, or maybe it's just a quick recap for all of you. And those who are not from CS background, it will be a bit new topics to you. So I will try to cover from the basics so that it is like understandable for all of you. That is kind of the thing. So the flow will be something like we will be starting with the problem, followed by the problem space, solution space, a few terms that is very much important or related to this thing. Just before we do the complexity classes, so which are like reducibility, decidability. We will also cover a part of the theory of computation or automata theory, as it is some way related to that. Then we will come to the Turing machine, followed by the undecidability. Likewise, that will be the flow. Okay, and then we will jump to the direct part. Okay, also I missed that. Meanwhile, we will be also covering a part of the asymptotic complexity as well. Okay, so that is something that we're going to cover, so that we have a good base of tomorrow's class, where we will be dealing with that why classical complexity or computational complexity is not really applicable, or how it is really, it will vary with respect to a quantum algorithm. Okay, so on that note, and also a special module I will cover, or a sub module I will cover today, just to show that how and why a problem is NP hard. Really, we will show the entire, we will try to visualize the entire solution space. We'll see that how it is exponentially growing with respect to the number of inputs if we increase them, and why it is really NP hard. So it was, if you remember the first class, if it was the fundamental of why we need quanta. So today we will see it in a bit of a classical context and bit of a mathematical context, or say algorithm context. Okay, so that is the thing. So let me start today's class. So first, you know that a general problem. What is a problem? If I ask you, a problem is something that has a certain characteristics, that it will be some sort of, there has to be a minimum two things, like one is the input to the problem, and there has to be a problem statement, right? Now, depending on the problem statement, it will have sum and the inputs. Your target is if you can map it to some certain output, right? So problem basically fundamentally, if I ask you what is basically you need, first you need a problem statement. If there is a problem, then definitely you should be having some problem statement of it, right? That is the definition of the problem. That is it. Then followed by, we will be having some input structure of the problem, that how we will be encoding the inputs. That is, what is the input and how you can actually, how to feed it, right? That is something that you should be knowing. So it is basically kind of a encoding of the inputs. And followed by, depending on both the cases, both the things, you should be getting some solution, right? So there has to be some solution. So from a problem, you have to define a problem statement. And from problem statement, you have to identify that what and how the inputs have been encoded into the problems or encoded due to the problem statement. And then we will see the solution. Now, during the encoding of the inputs, there is another thing that is very important. That is a problem space, right? So it is a problem space. Now, in short, what do I mean by the problem space is, say, a very small example I want to give. Say, I have told you that please add two integers. Then, adding to any integers is one problem. It is a problem statement. What your problem space can be, where you vary the integers. So, say, add 3, 4 belongs to the problem space. Add 8, 9 will also belong to the problem space. So, problem space actually has all the different type of problems there which need a solution. So similar to the problem space, you can definitely understand that there is a concept of a solution space as well, where we will be believing that there are several kind of solutions available. What do you mean by several kinds of solutions? Means there will be a different genres of solutions. Either it is a correct solution or it is an incorrect solution, or it can be a feasible solution or an infeasible solution. Likewise, all different solutions will belong to the solution space, right? So if I need to define that what is a problem space first, then I will slowly come to the solution space. It is a computational problem. A computational problem is a relation P, I'm marking it, I'll be asking you what is a relation, between a set of valid inputs, I, say that set of valid inputs is symbolically represented with a with a symbol I, capital I, and a set of valid outputs, which is say capital O, such that from now onwards I will be using this symbol for such that. Okay, this is a such that symbol. For each input X belonging to the input space I, the problem specifies what contributes to a valid output, say Y, where Y belongs to output space. Okay, so there has to be a correspondence between that. So symbolically, if I want to write it, so it's a P such that input I should belong, should map to output O such that X, Y, that is the input output pair as a solution, will belong to the problem space P. That is the definition of problem space. Okay, so that means a set of valid inputs now will be mapped to some set of outputs where this is your problem space, and wherever it is being mapped to is known as your solution space, where there will be different types of solutions available. Different types of your solutions. What do I mean by that? So solution type can be either a feasible solution, or it can be an infeasible solution, or it can be a correct solution, or it can be an incorrect solution. Okay. So correct solution, feasible solution means it will satisfy all problem constraints. So it will satisfy all problem constraints. So if everything is satisfied, we call it a feasible solution. An infeasible solution is if it just a minute. Let me remove it. Yes. So if it at least does not satisfy at least one will not be satisfied. One constraint. So if it is at least one not satisfied, then only we will call it an infeasible solution. It will fail the feasibility analysis. Third one is the correct solution, where we believe that a result output that exactly satisfies the problem. Problem specification for a given input. What do I mean by that? It means that it is feasible, that is meeting all the constraints, as well as it is also accurate. Accurate means that it produces the right answer. That is, it is following all the constraints, as well as it also produces the answer that it is supposed to produce. Then we call it a correct solution. So correct solution basically encodes the feasible solution as well as the accurate solution, right? So what is incorrect solution? What is your incorrect solution? So it is either it violates, an incorrect solution is a solution that either violates the problem constraints or fails to meet the expected output, or it can also be that it is not logically valid. Okay, so that means there can be different cases. First one is maybe there exists a logical error. That can also happen. Then it is an incorrect solution. For example, some bugs maybe in some algorithm. That also will lead to an incorrect solution. Second one can be a wrong problem specification. Wrong problem specification can also lead to an incorrect solution. Okay. Third one can be an incomplete implementation of the problem statement. So incomplete implementation is another one that leads to an incorrect solution in the solution space. And next one is the numerical imprecision. For a specific optimization problems, it is one of the challenges, particularly for few optimization problems where exact solution is needed. So in any way, the incorrect solution space can arise. Right? So for example, say example one, say sorting. Sorting means there will be some list or say some array of integers or anything. I have to sort it in some order. That order will be defined in the problem specification. So say I have to sort an array A, which is say 3, 1, 2, and I have to sort it in ascending order. So my correct solution is A 1, 2, 3. Feasible solution can be anything, maybe 3, 2, 1, 1, 3, 2, anything I can pick up, or say 2, 1, 3. Likewise, anything can happen. They are feasible. Why? Because they belong to the problem space. But are they incorrect? Are they correct? No. Though are feasible, they are meeting all the constraints. They belong to the problem space and all, but they are incorrect solution. Why? Because it is not in the ascending order. So not meeting the output specification criteria. Okay, so similarly, there can be another example, say a subset sum problem. Okay, where we believe that there is an input, say 3179, and I have given the task to find that which of these, which of the subset from this array will lead to some value of 10. Now their correct solution is, definitely you can understand, the correct solution is 3, 7 as well as 1 and 9. Both are correct solution. Right? So incorrect solution is 1 and 3. Why? Because 1 plus 3 is equals to 4, that is not equals to 10. Right? But feasible is, I can check 1, 3 as well. So they add values, they can add value that belongs to, and both of them belongs to solution space. Okay. But does not meet the target. What was my target? That is the obtaining the sum value 10. Now there is another concept that just comes after this, which is like optimal solution. Now for that, I just want to give you another example. Say I have this simple triangle, or it is a complete graph of 3 vertices, say K3. A complete graph of 3 vertices. Now, if I ask you that with how many colors I can color this graph? The graph such that no two adjacent vertices get the same color. Okay. Just tell me. So with how many colors I can color the graph? Now I'm giving you a few arguments. Say for example, with say 3 colors I can color the graph. With 4 colors I can color the graph. With say 999 colors I can color the graph. Say with a 1 million of colors I can also color the graph. Now, what about these things? All of them are solutions, right? Because with all these colors, I can color the graph. This is true. So all of them belong to the solution space. But if you notice carefully that this is some color which is not really, maybe practically also exist based on how many colors we can do, assuming that it does not exist. Okay. So something that does not exist will belong to your infeasible solution space or infeasible solution. Now, 3, 4, 9, 9, 9, all of them are feasible solution. Because with 3 colors, I can color the graph. With 4 colors, I can color the graph as well. With 999 colors, I can color the graph. In how many ways? With 3 colors, I can do it in 3C3 combination. With 4 colors, I can do it with 4C3 combinations. With 999 colors, I can do it with 999C3 combinations. But I can definitely color the graph. But if I ask you that, do I really need all the 999 colors or even 4 number of colors to color the graph? Can't I really color it with say red, blue and green with only using these 3 colors? The answer will be yes. So that means out of the feasible solutions, there are only a few solutions which are optimally feasible or which is optimal solution, right? So here, though 3, 4, 999, like these are feasible solution set, feasible solution say space where solutions are 3, 4 and 999, but optimally feasible solution space will look something like this, only 3. Why? Because with only 3 colors also I can color the graph. Right? So thereby there is an optimal solution coming into picture where we are targeting for something. Either it is that actually suits our problem objective. Okay. Now optimal is a very like generic term. It can mean anything. What do I mean by that? Say with respect to time. With respect to time, my optimal solution should be a minimal time finding. That means it is a minimal solution. With respect to cost, it will also be a minimal solution. That is, find the minimum cost or say minimal cost. But say with respect to throughput, it will be a maximal throughput. Okay. So with respect to say something like likewise the vertex cover, all those things, independent set, line cover, all these kind of things will have some maximum or minimum thing. Right? So if I told you like with how many minimum number of vertices is required so that if I pick up those vertices, all the remaining vertices which are adjacent to that particular selected vertex will be covered. So in that case, though I can take all the vertices of the graph, say for example, there is a graph like this, say any random graph, say this one. Okay. Now, if I say pick up all these things, V1, V2, V3, V4, and V5, if I select all of them, then definitely it covers all the vertices because anyway, in my cover, I have already chosen all the vertices. But if I tell you that I do not need to choose all, rather, why can't I choose, say I am choosing V1. See, if I'm choosing V1, that means V2 and V5 is already chosen. Now, if I choose, say, V4, what will happen? My V3 and V5 will also be chosen. So, V4. What if I say that with only two vertices, I can actually cover all the other vertices if my definition is that by selecting one vertex, all its adjacent vertices will be covered. If that is my selection, that is my kind of a statement, then with only taking two vertices, I can cover all. So it's kind of a minimum thing. So it is also an optimization problem where we are targeting to find the minimum one and choosing that as my optimal solution. So optimal solutions, say optimal solution set size for this particular graph will be definitely 2. It cannot be 1 because by selecting only one vertex, we cannot cover all the vertices. So it will be 2. So this is one of the optimal solutions. Now you might ask that is there exist any other optimal solutions? My answer will be yes. We just have seen that if we choose V1 followed by V3, if I choose them, because it is not a graph coloring one where by choosing V1, I cannot choose V3. I can definitely choose V3. So V1 will cover V1, V2, V5 and V3 will cover V2 and V4. V2 is already there, so I will not consider that. So V4 will be covered. So this is another optimal solution. So this is optimal too. Likewise, there can be for a particular problem, statement, we are choosing vertex for what purpose? I'm not going into the application part. It can be anything. You can think of the use case, but it's called a vertex cover problem where in graph theory, you might have heard of this problem where we target that with how many minimum vertices I can cover all the vertices of the graph. So it's kind of related to some degree of the vertices and all those things. It is not a graph color problem, it's a vertex cover problem. Both the problems are totally different. Okay. In graph color problem, the statement was that by selecting the criteria was by selecting one vertex color, if I color it with some color, then its adjacent vertices cannot be colored with the same color. Okay, so no two adjacent vertices should be colored with the same color. That was the definition for vertex graph coloring. But for vertex cover, it is if I choose one vertex, so I will assume that automatically all the adjacent vertices is already covered. So with by covering how many minimum vertices, I can actually cover all the vertices of the graph. That was the problem statement. So it's completely different problem. Okay. So, thank you. So we can see that there are multiple optimal solutions, which gives us the thing that for any problem and for particular instance of the problem, which is this one, say, instance of the problem, there can exist more than one optimal solutions. That's why it's called optimal. But if there exist, say, only one optimal solution, and with respect to vertex color, what is your optimal solution? That is the vertex cover size. So vertex cover will have the number of vertices that count will be equals to 2. We have seen that. So if there exists only one such optimal solution, say like only V1 and V4 is the only two vertex which will cover all and with a size 2, then that particular optimal solution will be known as optimum solution. Similarly, you can assume that out of many maximal solution, If there is any unique solution that satisfies the criteria, it will be called a maximum solution. So maximal means there is a possibility of more than one. And similarly, for more than one minimal solution, it's kind of a same thing where we will believe if only one satisfies our criteria. So that is called a minimum solution. On what? It depends on like what factor? It depends on the problem instance. Problem instance. Okay. So it can happen that there exists exactly one optimal solution or one maxima and one minima or multiple minimals and multiple maximal solution. That can happen. So if you're well aware of this thing, say I have a set of 1, 2, 3, then how many subsets of this set is possible? How many subsets are possible? Subsets of this set A is possible. What is the cardinality of the number of subsets possible? Please write it on chat. Yes, it's 8. It's 2 to the power the number of set. Now I'm not asking for proper subset, so it will be exactly 2 to the power 3, that is 8. I hope you are those who are telling 6, you are actually deleting the 5 and the full subset. Don't do that. I have not asked for proper subset. So total number of subsets will be 2 to the power 3, that is 8. So what are the subsets? That is 5. Then all the singleton sets. Then sets with exactly 2 elements. 1, 3 and followed by 1, 2, 3. Okay. And if I now say, so this is 2 to the power A. Now, if I say that I have to take a subset relation, subset mapping, subset relation, and I want to design a coset or a lattice for that. Not getting into that. Those who know it, you please map it. Otherwise, just look into it as a graph. So the subset relation that I want to map. So it looks something like that. So initially I start with say 5, which is nothing, okay, my empty set or null set. Then it's 1, 2, and 3, where we believe that 5 is a subset of all of them. Then 1 will belong to both 1, 3 and 1, 2. This is kind of a structure. Then 2 will belong to 1, 2 and 2, 3, and 3 will belong to 1, 3 and 2, 3. And 1, 2, 1, 3 and 2, 3, all of them will belong to 1, 2, 3. So this is a lattice where we believe, and it's a coverity relation. That's why I'm not taking 1 and 1, 2, 3. It's called coverity relation. Coverity relation, where we understand or where we assume that if 1 is a subset of, okay, say set 1, that's why I'm choosing the subset relation. I'm not choosing the belonging. Okay. So if subset of 1 belongs to 1, 2, and if 1, 2 is a subset of 1, 2, 3, then by transitive mapping, definitely it will imply that 1 will belong to 1, 2, 3, and this transitive, all the transitive relations are part of the coverity relation. We believe that this particular relation, that 1 is a subset of 1, 2, 3, is already covered. So we need not to put a explicit line showing the mapping between 1 and 1, 2, 3 in the lattice diagram itself. So we actually have ignored, or it is hidden, all the coverity relations is hidden from this, assuming that thing where we only are mapping the direct relation, no transitive relations we are mapping, assuming that if you see there exists only one maximum where anyone you choose, they will be mapped ultimately to this one, 1, 2, 3. And this 5 will belong to the minimal thing. So this is the lower bound, or say greatest lower bound and least upper bound kind of thing. Okay. So this is finally the maximum. It's the final upper bound. And this is the minimum. That is the lower bound. I have drawn this diagram so that I can just tell you diagrammatically, if you see something like that, it will cover some extreme relation, which is the extremum is there, either maximum or minimum. But if you see something like that, say A, then BC, what is the relation? I'm not getting into that. Say likewise, you are getting say CE, or say EF, kind of that. Any relation. What it is, I'm not going into that. EF and say GH, something like that. If you see something like that, then you will understand that there is minimum element is there, but there exists no maximum. Only two maximal is there. And they are EF and GH. Just to tell you that I have just shared this thing. Okay. So that is the thing. So now after you have got till this part, you should be having some understanding of what is a problem, what is a solution, what is a problem space, what is a solution space. Then followed by, you should have some understanding of at least the feasible solution. Feasible solution is something which is possible but need not to be accurate. Then you have seen the infeasible solution, which is not really possible based on the input or the problem instance given to you. Then you have seen the correct solution, where it has to be at least feasible, followed by it has to be accurate as well. Accurate means whatever is the objective function, it should satisfy that. Then it is an accurate solution. And also the incorrect solution, where either it will fail in some way, one way or the other. So it's infeasible, or it's incomplete, or it's an incorrect problem specification. It can be any of these cases, right? So these are the possible scenarios. Now say with respect to traveling salesman problem, where what is the problem statement? For any problem, we should start with the problem statement. So what was the problem statement of traveling salesman problem? That a salesman needs to actually start from one city and eventually had to cover all the cities. But the criteria is the salesman can only visit one city exactly once during his trail. And post that, he ultimately needs to come back to the starting vertex. And this problem, in mathematical term, it is called a Hamiltonian cycle. And the tour is Hamiltonian tour, and the cycle is known as a Ham cycle or Hamiltonian cycle, where the criteria is age can be repeated. Age can be, not visited. If age is repeated, anyway, vertex will be repeated. So it can be not visited, but every vertex has to be visited, and a vertex can be visited exactly once during a Hamiltonian tour. Then that is called a Hamiltonian cycle. TSP is basically this particular thing. Now, what is our target? Say, for example, there is a cost associated, say 10, say 12, say this is 6. I'm considering an undirected graph with any random one. Say this one. Okay. So this is a starting vertex. So I can come back to this particular S by any possible ways. Okay, say S, A, B, C. So either S to A to B, B to C, C to S. So S to A to B to C to S can be one solution. What will be the cost? Say 10, 20, 6 and 4. That can be a cost. So it's 30 and 10. So 40. Right? Or it can be S, say, what it will be? It will be a repetition. Okay, I have to cover that. For this, I guess it is only one solution. But I'm just assuming, just a minute. Let me assume that S to B, there is a path here. Just I'm assuming this thing. So there is a path, say it is 16, and that is S to S to B, I will be going first, then to A, then to C, then to S. So both are feasible solutions. Both are feasible solution. You can see there is a path and you can traverse through that path. So that is feasible. So S to B is nothing but 12, B to A is 20, A to C is basically, A to C is 16, and C to S is 4. If you add them, it's 20, 20, 40, and 12, that is 52. So both the cost 40 and 52 are feasible solution, but definitely you can understand that with respect to cost, as I was stating, that with respect to cost and time, our optimal solution will always aim to or point to a minimal solution. So that means your feasible solution set will cover something like S, A, B, C, S. Following there is a path. Okay. And S, B, A, C, S. Both of them. But optimally feasible one, that one is your S, A, B, C, S. That is the first solution. So optimally feasible is it belongs to the feasible solution space, but that count is more than one is a possible one, but it will be not all of the feasible solutions in general cases. Right? So that is the target. Now you might ask, I hope I do not need to mention again that why I cannot go from S to B, then to A, then to S, then to C or S, something like that. Why I cannot do that? Because then it will be a repetition of the vertex S. And in a Hamiltonian cycle, I'm not allowed to do that. Age I can repeat, but generally by repeating age, for unless and until there is a very particular case, otherwise the vertex will be repeated. So we cannot do that, but if needed, we can skip some of the edges, but every vertex has to be covered and that count has to be exactly equals to 1 except the starting vertex where I have to come back. So except the end vertex and the source vertex, there will be no repetition. That is a Hamiltonian cycle. So what can be the incorrect solution space covered for this one? So the incorrect solution space can cover that I might miss a city, that is skipping a vertex, say, or I can revisit a city, which is repetition of a vertex. So all of these solutions will lead to an incorrect solution. Third one is does not return to start. Okay, that means like not a ham cycle, at least that criteria is not fulfilled, or it is not the least cost, when optimality is considered. Okay, can there be an infeasible solution here? Absolutely. Say this thing, either this one or say this one. In both the cases, say this is my starting vertex, S. So this is A, B, C, and they say D. So that means it is an infinite cost. So it's an infeasible solution because the path length is infinite. Is it an infeasible solution? Kind of. Also, it is an incorrect solution. Why? Because here ultimately, anyway, I have to, after visiting D, since I have to come back to S, so that will be infinite. So in that way, it is infeasible, and it is incorrect because if I do not take back this thing like D to S, ultimately I have to again traverse back to C. So in that form, so because of infinity, it is infeasible, and because of a edge vertex repetition, it is incorrect. Okay, so that covers our first phase when we have learned about the problem space and the solution space. Now, till this part, just tell me, is it okay? Till this part. So today we will be covering in different phases our entire context. Okay. Anyone has any question on that? Okay. Okay. Yeah. Is it okay? Then I will go to the next submodule. And also of incorrect solution. Do we need them? Okay. What was your question? First question, I missed it, Mansi. If you can again put it on chat. I don't want to stop sharing. Or if you have any question, we can also do it at the end. Or you can also put it on chat once again. Sorry, I missed it. The first part. We're asking something on the incorrect solutions. That we need to keep track of incorrect and infeasible solutions. No, this is not keeping a track of. I'm just describing the solution space. Now, with respect to a small problem, it might be something. Okay, that it might not be some very relevant one to you, but for a very complex problem statement where it incorporates some multiple parts of this problem objective which you have to cover, and there is a feasibility of one part is somewhere related to the other part, then you have to analyze what can be the incorrect solutions as well. And also for testing purpose, you have to do that. That is another thing. Okay. 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 So now, next, let me start the second part, second module. So first module was over. So second part is a bit of the automata theory. So those who are well aware of a bit of automata, you know that it is nothing but some abstract machine. Okay, some abstract logical machine that works on some input and is already in a particular state, and on both these things it will yield to some output. Okay, so it's kind of an abstract machine that either accepts or rejects some language based on primarily two things, that is some state or current state information and the inputs that it is processing when it is in that particular state. So formally, the definition is of an automata or a machine is, automaton or a machine is this thing. So Q, sigma, delta, Q0, and F. This is a 5-tuple form where Q is a finite set of all states. So it's a state space kind of thing, right? This is a set of input alphabets or finite set of input alphabets. That is a set of terminals. Terminals means with which we end a particular language acceptance or rejection, whatever it is. This okay, let me write Q0. It is the initial state of the automata, where Q0 belongs to this Q. This F, it is the finite set of final states. Okay, where F is a subset, either a proper subset or it can also be fully a subset of Q. This means when F is equals to Q means that all states are my accepting states or final states or terminating state, whatever you say. And what is my delta? Delta is a transition function where delta is nothing but Q cross sigma. It will map to some delta, some Q. Or you can call it Q star. Okay, so that is, what do I mean by this thing? So transition function means on being a particular state Q, on having some symbol sigma, I can go to some other state which also belongs to the finite state set of states Q. That is the definition. Now, based on this definition, there is a hierarchy for all the grammars. I'm not going into the depth, I'm only covering the connecting dots, which I require for the complexity analysis. Okay, so that is called Chomsky classification of grammars. So there, it is something like that. So it's a type 3 grammar, then it's type 2, then it's a type 1, and this one is a type 0, where this is called regular grammar. This one is called a context-free grammar. This one is called a context-sensitive grammar. And this one is called a unrestricted grammar. Where regular grammar looks something like this, say A2 alpha beta, okay, or it can be A2 alpha. And it can be recognized by a finite automata. Finite automata. Precisely telling, it's a deterministic finite automata, DFA, or a NFA. And language accepting power of both DFA and NFA are same. So I'm writing it in this way. Second one is a context-free grammar. This one. It is also known as a type 2 grammar. Okay. So context-free grammar looks something like that. Let me write it here. Say type 2 or CFG, context-free grammar, how it looks like. So it's a A2 alpha, where A is definitely a non-terminal. A is a non-terminal, and alpha belongs to a set of NT, or say non-terminal, union terminal, any combination of that. NT, union, T, star. That is, it can be null or it can be anything. It can be only a non-terminal, it can be only a terminal, it can be Non-terminal followed by some terminal, or it can be terminal followed by some non-terminal. It can be anything. But the condition is in the left-hand side, it will be only exactly what non-terminal, which is represented by this thing. Okay. And these type of grammars are recognized by push down automata or PDA. Okay. Okay. I'll pause here. It's already 3. I'm just giving you a 2 to 3 minutes of break. Then we will cover the type 1 and 0, and we will enter into Turing machine and the definition of complexity classes. Just a 2 minutes of break. Okay. It's 3. So it's 3-1. We will meet around 3-3 or 3-4. Kind of. Is it okay? Thank you. Thank you. Thank you. Yes. Mm, this class. Yeah. Let me start. Sorry, I'm a bit late. Yeah. So, yes. So this is type 2 grammar, as we have seen. So we'll start with next type, which is type 1 grammar or context sensitive grammar, where it is of type this alpha A beta will be mapped to alpha gamma beta with the length of gamma, this thing can be greater or equals to 1. Okay, so this type of languages are accepted by linear bounded automata. Or LBA. Okay, and the next type is type 0, which is also known as unrestricted grammar. Unrestricted grammar, where there is no restriction in the LHS and the RHS. So the rules are alpha to beta, and there is no restriction on what can be present in the LHS and the RHS, but only condition is LHS cannot be null. Alpha cannot be equals to null. Except that there is no other restriction. Okay, and these are the languages accepted by our Turing machines or TM. Now that we at least have arrived till Turing machine, so we will start with that. So you can understand that we believe, with the term unrestricted also you can understand that we believe that if there is any type of grammar, then we should be able to process it, or there exists a machine that can process it, and that machine is known as a Turing machine that we believe that we have. So definition wise, a Turing machine is a seven tuple form of description, where we believe a TM, say, has these features like Q, sigma. What is Q and sigma? You all know, set of states, set of input alphabets. Then this is a set of tape symbols, and this is a delta, then a Q0, then two states like Q accept and a Q reject. So these are both halting states. That is, on getting this thing, it will either halt in both cases by accepting or by rejecting. So Q0 is the initial state, and this is the tape symbol. Now tape symbol means it is either a left or a right, kind of that. Okay, so what is the current context of the tape that it has? It has a input tape. Based on its input and based on the symbol or the state that it is in, it will map to some state, will put some or change some tape symbol, and either will remove or say move the tape head to either left or right. That is the three things is there. First is, so delta, this transition function works in this way. So delta on having Q and sigma will be mapped to this thing Q, tau, and this L and R. That is, either it will move the head to a position left or right. I understand. I really understand. See, I understand. There is going to be some difficulty of yours understanding it, because there is a kind of automata theory here, a reducibility, a high-end algorithm part is there, and as well as a computational complexity parts. I totally agree. But please just, what you can do is, what I can suggest is, I hope by today's class and tomorrow's class, we'll be having a better picture of this thing. And at least by end of today's class, you will be understanding that what are the several components. Maybe Mansi was asking that what is the context of today's class. Today, officially, we are going to only speak about P and NP, and NP had an NP complete and co-NP maybe maximum. But if I just give you these definitions, you will anyway not be understanding anything. Okay, because all of them are related to problem, then problem space, reducibility, Turing machine, then decidability, undecidability. A lot of components is there. Okay, so only that context which might be helpful for us to understand it as a maybe a newcomer also will understand it. I'm telling it. But those who are completely from physics or completely from electronics background, they are going to really be, it is going to be very difficult for them. Just hold on for some time and have some patience. Reading reference paper. Absolutely. So what are all the topics? First is I will be giving you the notes itself during the class itself. You can take the notes. All the definitions are all we will be covering. I'm not covering the details of automata. I'm just deriving till the Turing machine part. I'm just deriving till the Turing machine part. Okay. Otherwise, I cannot enter directly into the undecidability and the decision problem, optimization problem very well. Okay. So there is a clear-cut some dependency of the topics. One way or the other, logically, sequentially, there is a dependency. Okay. Please hold on for some time. After 15 minutes, we can do a knowledge check and we will see that if we have understood it correctly or not. I'm not going into the definition or much details of the automata. I'll skip that. No issue. Okay. Because I have to take you through the deterministic and the non-deterministic Turing machine. Otherwise, I cannot tell you the P and NP. And I'm just right now entering into that part. So this is the definition of Turing machine. Now, Turing machine is of two types. First one is the DTM or a deterministic Turing machine. So deterministic Turing machine, deterministic, if you remember this word, I have been describing it from the very first class, that deterministic is one transition per state symbol pair. Okay, so there is a one-on-one mapping that is called determinism. So that means one transition, only one transition per state symbol pair. That is, if I am in one state or having some input, I can only reach to one state. Simple words, there is a one-on-one correspondence. And a non-deterministic Turing machine is another category of Turing machine. Non-deterministic Turing machine is what we have seen, that there exist multiple transitions, more than one transitions possible, and it accepts any path leading to acceptance, leading to Q accept that thing, that this final step. It will follow any path. Means, say if this is my Q accept, say these are three possible paths. So this particular phase is a part of a non-deterministic process. This is an ND process, non-deterministic process. Because see, if I choose, say, from S to A to B, it's a solution. S to C to B is a solution. S to D to B is also a solution. So that kind of Turing machine is considered to be more powerful Turing machine than a deterministic Turing machine. But honestly, in terms of language acceptance, in terms of language recognition power, that is, if I give any language does not mean your English language or Hindi language. It means your computer compatible language, which is maybe unrestricted grammar generated language or any language. Okay, that's a part of this thing I'm referring, consisting of a non-terminal and terminal. So using that, what finally terminals we are getting based on that. So if that particular language is there, which is accepted by a non-deterministic Turing machine, it will also be accepted by a deterministic Turing machine. So few things I would advise you as of now to take it as a theory, or as of now take it as a like protocol. Just assume they are true. Based on that assumption, please follow the next one. Reject is also possible. That is, I will be in a halting state. That is the thing. Leading to acceptance means leading to rejection as well. I will then come to the halting problem. That was my target. Okay. So just assume two things. Bit of comparison between this NTM or NDTM and DTM, deterministic Turing machine, and non-deterministic Turing machine is in terms of language acceptance power or language recognition power. Both are same. If you have NDTM, you can convert it to DTM in order to accept or in order to make a language being accepted. But with respect to time complexity, this is feature 1. The feature 2 is with respect to time complexity. If you notice, then if its power is say P1 and its power is P2, then P2 or say P1 is much less than P2. There is a power that P1 has, or the NDTM has, DTM has, is much less than the power that the NDTM has. That means the time complexity more powerful means takes less time. So the time complexity of DTM is much higher than the time complexity of NDTM. So more powerful is taking less time, and less powerful will take more time. Just like that. Okay. Okay. So just take an example of that. Say SAT problem. It is called satisfiability of Boolean formula, or satisfiability problem for Boolean formulas. So LSAT, language that accepts the SAT problem, something like that. Say phi, where phi is a SAT. Say example, sorry. Say example formula can be, say phi is x1 or negation x2 and x2 or x3. I hope you know this is nothing but, if you want to write it in this way, x1 plus x2 bar into x2 plus x3. Any form you favor. Okay. So that is kind of a problem. So I have to find a solution for x1, x2, and x3 which satisfies this thing. That is the SAT problem. Now, if you see very carefully, if there are like three variables, okay, then if I give you a solution, say I'm giving you like x1 is equals to 3, x1, x2, x3 all can be either 0 or 1. If I give you say x1, x2, x3 as 0, 0, 1, and if I tell you that whether this is a solution or not, then you can actually do it in very fast time. It will not take much time. But if I tell you that out of the possible solutions, please find a solution so that it satisfies this equation, then it is going to be a bit difficult problem. Okay, it is going to take a bit more time. That is the thing. Because why? Because it is a brute force. So brute force of any approach is basically a kind of a hard problem. It's a bit of difficult, where we have to explore all solutions. There is no way we can reduce the number of queries or number of counts. So the NTM, on that note, the NDTM or NTM for SAT definition wise is something like that. So first, it non-deterministically guess truth assignment to all variables. Okay. What I'm talking about, just remember, I'm talking about non-deterministically. That means all possible solutions in a multiple way it can explore. It's an NDTM. That's a different thing. That what is a practical interpretation of this one, or have you ever seen that? That is our next phase of question. But we are assuming there exists a Turing machine that has a non-deterministic power of computation. So that is an NDTM. And for satisfiability problem, if it exists at all, the NDTM, it will work something like that, that it first non-deterministically guess or guesses truth assignment to all variables. Second one is, it can verify whether the formula, after assignment, it will directly verify, right? Whether the formula evaluates to true. That is, whether it's coming a tautology or not, after putting all the values of x1, x2, x3. Okay, true. Under that assignment, right? So if any guessed assignment satisfies the formula, it will accept it, right? That is the logic. So that means guessing is order of n. Okay. Now, verifying is also or in order of n for an n variable set. So in total, for guessing and verifying, in total it will take order of n time, because it's ultimately some constant here. And just to tell you what about the big O notation, this is called a big O notation. This is a part of the asymptotic complexity. So if a function is like, just a quick note, I want to talk about the big O notation also. So if a function is like, say 4n square, or say n cube, plus 3n square plus 7n plus 5, then we will assume that this 4n cube plus 3n square plus 7n plus 5 is definitely less than equals to something, say 4n cube plus 4n, say all of here in all these spaces I'm assuming n cube. Say I'm writing c1, say c1 n cube plus c2 n cube plus c3 n cube plus c4 n cube. I can do that because 5 ultimately is less than c4 n cube, 7n is less than c3 n cube, 3n square is definitely less than c2 into n cube, likewise for a large value of it. So initial few values I'm ignoring them. Okay. So if that is the case, I can write it that all this thing is nothing but c cap or c prime into n cube. These are accordingly adjusted somewhere. I also do not know what is the values of c1, c2, c3, c4. Also, I do not know what is c hash or c prime, but I definitely know that considering c prime adjusts all the coefficients c1, c2, c3, and c4, it can be somewhere c hash n cube. So if I am able to write that if I'm able to write this if, which is a left-hand side if, in this way, then we can imply that if not equals to, remember, it belongs to some big O of n cube. That means if is less than equal to some constant into n cube, that is n cube is the asymptotically, it is higher than f. That is, it comes under n cube. The maximum possible complexity that f can have is n cube. And it belongs to the complexity class of n cube. Okay. This is what we will be assuming. So similarly, if I ask you that what about n and n square and n log n and log n, you know, asymptotically there has a relation because log n is less than n is less than n log n and is less than n square. So likewise we can write. So if our equation has, say if Fn is C1 into log n plus C2 n square, then I will say that Fn belongs to some big O of n square. Okay, there is a maximum one I will be talking. I'm not going into the omega or the lower bound. This is called the asymptotic upper bound. Okay. Now, similar to that, if I tell you that what about if something is n factorial, then what it is? What will be its big O? If you notice, n factorial is nothing but n into n minus 1 into n minus 2 into n minus 3. Likewise, it is still either I can end at 1 or I can end at 0 anyway. But if I'm writing it in this way, it is better to end at 1 because it's a multiplication itself. Okay. The 0 factorial is also 1. So in that way, it will be 1. Okay. So if that is the thing, now can I write it in this way that n is less than equals to n? Is it correct? Yes. N less than equal to n is a correct statement. It's the truth. Okay. So now can I write n into n minus 1 less than n into n? Of course I can write because n is less than equal to n is correct and n minus 1 is definitely less than n. That is also correct. So step 1, step 2, step 3 is say n into n minus 1 into n minus 2. Can I write they are less than n into n where this n in this n, this n minus 1 maps to this one and this maps to this. I can write it down. Both are truth, like both are tautology, like all of them are tautology. Likewise, if I write n into n minus 1 into n minus 2 dot till 1, this is less than n into n dot till n, where this also is 1 to n, that is n times, and this one's also n to n, that was also is n times. Then this is nothing but n factorial. See, this is the definition of n factorial. So this is less than equals to, what is the value? N to the power n. That means n factorial belongs to big O of n to the power n. It itself is a class to talk about asymptotic complexity. I'll not go much of it, but at least just to tell you that we always take the higher value. And we do not generally write it equals to because they are never equal. So they belongs to the complexity cases. So please use the symbol belongs to. Okay. Now, where we initially were, we were in a non-deterministic Turing machine for SAT. So we have seen that if we at all are able to process all the solutions, we are able to guess all the solutions to all variables simultaneously, that is non-deterministically. And then after that, we will verify by putting the assignment to each of the cases. Then we will see that they are verifiable as well as we can guess the solution both in big of n time. That is for a non-deterministic Turing machine. But if I have a deterministic Turing machine, DTM, for SAT, now you can assume the way we do it, how we will be doing it. We will be doing a truth table of that x1, x2, x3. We'll put all the values 0, 0, 0 till 1, 1, 1. Then part by part, we will calculate x1 or x2, then x1 and negation of x2. Likewise, we will be calculating. So that means for n variables, how we think deterministically, that is, if we want to compute, we will be computing all the 8 assignments, 2 to the power 8 assignments. All combinations of 0, 0, 0 till 1, 1, 1, we will be putting in x1, x2, and x3 respectively. And we'll then check that whether that is coming true or not. So we will be here, we will must try all 2 to the power n assignments one by one, then evaluate the formula. Okay, so evaluating the formula will be order of n, no issue, but trying all of them will take order of 2n. So the time it will take is, it will somewhere be coming as order of 2 to the power n. Okay, so we can see that satisfiability, it is in NP. Okay, so sorry, so we have seen that SAT can be easily verifiable in polynomial time. Polynomial means polynomial time. Polynomial means what? That is something of n to the power k form, where k is nothing but some integer, or say any number, or say better is to write not a function of input. Okay, so SAT can be easily verifiable in polynomial time. Okay, considering we are verifying using a NT. But not known to be polynomial time solvable by this DTM or deterministic Turing machine. Okay. Now, the next part is what we call a decidable problem. So a decision problem, for that, first let me tell, a problem, we have understood that problem can be of two types. First one is a decision problem, which has a solution, kind of yes or no. Then we call that problem a decision problem. And another one is a optimization problem. Where it's about finding a solution. So it's basically kind of checking a solution. And this is about finding a solution. So, okay. Now, a decision problem is said to be decidable if there exists a Turing machine. Alternatively, this means an algorithm. If there exists an algorithm, as per the definition of Alan Turing and its theory, that there exists a Turing machine. So if there exists a Turing machine or an algorithm that always halts, that is, halts means, that is, it finishes in finite state, or it means it will stop working after a particular time and correctly decides after halting, and it correctly decides whether any given input string belongs to the language L or not. That means it will answer as yes or no. Now you understand that why for decidability we need decision problem, and decision problem description needs a Turing machine. Okay, they're very much related. So that is called a decision problem. So definition wise, a language L, we'll write it something like that. A language L belonging to sigma star is a set of input symbols or alphabets, is decidable if there exists a Turing machine such that machine with some input W is equals to accept when if W belongs to L and if MW will return to reject if the string does not belong to L. This is a definition of a decidable problem. Now next one is a say not going further in the definition of or the example of decidable. I hope you understand. So say for example whether a string is palindrome or not. Okay, or whether particular string or say input ends with the symbol AB or not. Everything, anything that any grammar can do, Turing machine can also do. And if it produces some answer, yes, no, it is a decidable problem. So an undecidable problem is something where there exists no Turing machine that can decide that for all possible inputs, if there exists in a Turing machine or not, that always halts with correct answer or not. So it is unable to decide that whether for all possible inputs, there will be some Turing machine that will perfectly halt or not. It is indecisive to answer that. That kind of problem is known as undecidable problem. So it means that a problem, let me write the definition now. So a decision problem is undecidable if no algorithm or say Turing machine exists that can decide if for all possible inputs there will be that can decide that if for all input there will be some Turing machine. Just check the definition. I hope you have got the meaning. So if no algorithm exists that can decide for all possible inputs, there will be some Turing machine that will always halt. So it's a negation of this thing. No such algorithm exists. Always halt with correct answer. Okay. So L belonging to sigma star is undecidable if no Turing machine exists which halts on all inputs and accepts all strings in L and rejects all strings which does not belong to L. No such Turing machine exists. If that is the case, then that language is called a undecidable problem. That problem is called an undecidable. Okay. The perfect example of undecidable problem is also very important. This is a halting problem. What does it state? It states that given a Turing machine and the input W, given a TM and an input W, does M halt on W. Only this is given. So you cannot have a precise answer to this. You do not know whether after some time on your input, the Turing machine will halt or not. Since you are unable to tell that, or there is no such Turing machine that is able to confirm that yes, it will definitely halt on any input W, then this type of definition is called a halting problem, and that particular problem is known as an undecidable problem. Okay, so it is something like this. So problem definition of halting problem is, say, halt P or halt M, machine halt, okay? Then M will halt on W. That is the problem statement. Formal definition of the problem is. Okay. So this is part 2 of the component where we have seen what? We have seen this thing. We started with the Chomsky classification of grammar and automata theory. And then we have seen all the 4 types of grammar. Primarily, our aim was to focus on the unrestricted grammar of Turing machine. Then we have seen the 2 types of Turing machine, non-deterministic and deterministic one. And we have analyzed the differences with respect to the language recognition power, where we believe that both are same and there is equivalence between them. Okay. Second one is the time complexity, where we believe that the NDTM is more powerful than DTM. That means the time complexity or time needed by NDTM is less than that of time needed in DTM. Okay. Then satisfiability problem is one classic example that we have seen. In order to explain that, we have gone to the asymptotic complexity classes. We have covered only one such class, which is big O notation. We have covered then few examples on how to compare them. And we've seen a few examples. Post that, it is a DTM for SAT, how it works for the verifiability and the solution finding cases, both the cases. Then decidable problem we have seen. Okay, then we have seen the decision problem and optimization problem. Decision problem is finding a yes or no or checking a solution. Optimization problem is finding a particular solution. And then we have seen the definition of decidable and undecidable problem. Okay, and then the famous example of halting problem. So all these things we have seen. So this is submodule 2. Third one is a very small one that we will enter into the complexity one. Okay. So before that, only small thing is the notation. You should be well aware of it. It's called a polynomial time reducibility. I'm not getting into much of the reducibility or reducibility theory. Just I want all of you to know the symbol and what does it mean. So polynomial time reducibility. Okay. What do I mean by this and how to represent it? These are the 2 things we should be knowing. So we say a language A is polynomial time reducible to B, that is, we write it in this way, and it means that A is polynomial time reducible to problem B, or language A is polynomial time reducible to language B if there exists a polynomial time computable function, polynomial time computable function if such that for all input x, if x belongs to A, it will both way imply that fx will belong to B. There is a correspondence. Then f is called reduction from A to B. Okay. So this is this one thing, just remember. So now the complexity classes, I hope now all the components you will be knowing. All components you will be knowing. So P. Now we are entering into the definitions of the complexity classes itself. We are those complexity class where we believe that there exists a polynomial time solution to a particular problem. What do I mean by that? There exists a polynomial time solution. That is, I can find a solution to that particular problem in polynomial time. So P is polynomial time solvable problem. Alternatively, we believe that there exists a polynomial time solution to the problem. Alternatively, we can also say that in a deterministic Turing machine, solving or DTM, solving that problem will take polynomial amount of time. Alternatively, we also can say that this P is nothing but polynomial time. This is also true, or the better version will be deterministic polynomial time, because they are solvable in polynomial time by a deterministic Turing machine. Okay. So next one is, this is the case 1. 2 is example of this one, anything that you see. Anything that you see where like finding the shortest path where there is a polynomial solution. Say binary search, linear search, sorting, everything where there is a polynomial solution. It's a P problem. Then what do I mean by a NP problem? Similarly, I will be writing the definitions. So it's a non-polynomial time solvable problem. That is the first interpretation. Let me write. So it's a non-polynomial time solvable problem. Next one is, there exists a non-polynomial time solution to the problem. Let me write. There exists a non-polynomial time solution to that problem. Third one is, in a deterministic Turing machine, solving that problem will take polynomial amount of time. Let me write. In a DTM, solving the problem take polynomial. No, this is wrong. So it will be non-polynomial time here. Now here is a twist. That is, there is another point that we can add. That is, in a NDTM, solving the problem will take polynomial time. No, in DTM, it will take non-polynomial time. In NDTM, solving that problem will take polynomial time, average. What was the last interpretation? That was P is nothing but polynomial time or deterministic polynomial time. But here it is NP. So NP is nothing but non-polynomial time or non-deterministic polynomial type. Now you see that why it is a non-deterministic polynomial, and of course you understand this is the Now the thing is that why it is non-deterministic, because in a non-deterministic Turing machine I'm referring, that is why it's non-deterministic. And why polynomial, you now know the meaning of polynomial, right? So that is why understanding a Turing machine is very much of a like a primary concept or primary base for understanding the complexity classes. It's all about not only the problem or the algorithm or the time complexity that we are getting, it also depends on what machine I'm getting that time. Am I using a really powerful machine or am I using my normal machine? If I'm using my normal machine, it will take a non-polynomial. Normal machine means the machines that we have. Now you will be asking the question that if in a NDTM it takes a, might we take non-polynomial time given that P is a subset of NP? It's not really very well defined, but we just assume that P is a subset of NP. Is P is a subset of NP? Is P is equals to NP? That is something that is not yet solvable. But we believe that maybe P is a subset of it. That is just our belief. But the thing is that, see here, a little analysis is required here. That means if I have, say I can have two different types of machine. First machine is a deterministic machine. That is on one input, one state produces one output. That is all the classical machines that we have. And if I give a very complex problem, okay, then how much time it will take? It will take a non-polynomial. It will take a non-polynomial time. Non-polynomial time means nothing but an exponential time. Okay. Also, let me write it. Non-polynomial is nothing but exponential. Means it is something of the form k to the power n or n to the power n, where n or the input size is in exponent. Input is in exponent. No, not really. Not really. If P is a subset, if P is equals to NP, there it can be both way provable. Like if P is a subset of NP and if NP is a subset of P, but we have not got any case where we have seen that P is not a subset of NP. That is why, based on an experimental analysis, we only say that maybe P is a subset of NP. That is only our assumption, what our assumption is. Okay, but we has considered it to be true because we have never seen any contradiction. So when we say something is equals to something, A is equals to B, when A is a subset of B as well as B is a subset of A, then only we say that A is equals to B. But in order to prove that, we have to prove it both ways. But we have never seen any case that where P is not a subset of NP. But still the work is going on, but definitely experimentally, it is confirmed that it is a subset because there is no contradiction yet. Okay. And the Venn diagram that we draw and everything, that is based on that assumption itself. We are assuming, because still date we have not got any contradiction, so that's why we put that P within the NP class. So it's something like that. Something like that. But again, what I was talking, that if I have a non-deterministic machine, then finding this thing would be possible in polynomial time. And what is a non-deterministic machine? Do we have any non-deterministic machine with us? Yes, we have now. That is a quantum machine. No audio. Am I not audible to others as well? Audible. Yes. Audible. Okay. Thank you. Thank you. Okay. Thank you. Thank you. Okay. So if we have some non-deterministic machine, which we didn't have till date, so we believe that it is a non-polynomial solvable problem. But if we have a non-deterministic machine, then it will be a polynomial type solvable problem. That is why we call that all the hard problems right now in quantum, they can have a polynomial time solution, or there can be an exponential speed up. Okay, I'm not getting into that non-deterministic calculations, whether it's iterative, it's generally all the brute force. Now, if you want to say iterative and brute force equivalently, you can say that, but it's mostly the brute force approach where I have to, like trial and error, I have to pick up a solution, then test, then again pick up the next solution, then test. Likewise, I have to proceed one by one, likewise. Okay, so that is AP and NP. Now, the third one is your NP hard. NP hard. No, I'm not really talking heuristic. I'm not really getting into the heuristic. Heuristic is, I guess, something a bit different version. So NP hard is something. So you can consider it in this way. Before writing the mathematical definition, let me just tell you in this way. Say you have a class of students. Okay, say a computer science batch of say 2025, CS batch 2025, and all these are all the students. Okay, say this particular one is the topper of CS. Okay, now an IT topper has came to class, and she is claiming that no matter how best you are or how good you are, I am at least as good as the best versions of yours. So I am at least as good as any one of you. What she is claiming, that I am at least as good as any one of you. Okay, what does it mean? That means even if you pick up the topper of CS, she will be performing the best than rest of the CS students. It can be assumed. Now IT topper is claiming that whoever performs the best, I'm at least as good as them. So my performance is greater or equals to the performance of any of your students. That is the thing. Now, if I replace students with problems, say the equivalence I'm now mapping. Say all of these are problems. This is a problem space. What this problem space is known as? Say NP. Okay. Say it is L. L is the new problem, IT topper. And these are all the problems. Okay. So what L is claiming now? What is the claim of L? L is claiming that for all L dash belonging to NP, L dash is polynomial time reducible to L. See the definition. Just understand why we have done all these submodules, polynomial time reducibility and all this stuff. So this is a for all symbol. So for all L dash belonging to NP, that is for all students who belong to CS batch, you pick up any one of them. So she is or he is reducible to me. That is, whatever she can do, I can also solve. Or whatever, how much hard it is, what it cannot do. So I am actually stronger, kind of stronger than any one of you, where you is that one is the L dash. No, it is not a subset of L dash. Nothing. If it is a subset, I would have written it within the circle itself. So if there exists a problem L which is claiming that I am at least as good, now replace good as hard with hard. So if L is claiming that I am at least as hard as any of the problems that belong to NP, no, L is not one of the L dash. L is not one of L dash. Just wait. You are mixing two very similar things up. I will come to that point. L is not a subset of L dash. Okay, focus on the definition now. So the claim is if L is at least as hard as any of the problems belonging to NP, this is the mathematical definition, then L is called NP hard. So this was the definition of L. L is equal to NP hard. Okay. Now the cases that you guys were talking about is the fourth case. So NP hard does not belong to NP. Okay. So that is the fourth variation, which is NP complete. So it is that these are students, okay, or so these are problems that is in NP. This is your L dash, say somewhere here. Sorry, L is somewhere here. And all these other problems are say L dash. And the claim is exactly same with a bit of modification. That is, L is NP complete if L belongs to NP and for all L dash belonging to NP, L dash is polynomial time reducible to L. When both of them are true, then it will imply that L is NP complete. This is the definition of NP complete. So that means NP complete problems are those problems which are definitely NP hard. So don't go into that part that it is NP hard or NP complete or what it is. So NP hard means it is at least as hard as all problems belonging to NP. But it also is verifiable in polynomial time. That means it is also in NP. But finding the solution is going to be very, very hard. So those problems are NP complete problems. With a small example, I can give you some solution to tell that. Say, let me give you example, then you will understand. Okay, the one who was just telling that it also belongs to NP. Are you convinced now that that was NP complete, NP hard, where that problem, which is at least hard as any problem, and all problems is NP is polynomial time reducible to that problem, then that new problem was NP hard. But if all problems in NP is polynomial time reducible to another problem which also resides in NP, then we call that problem as an NP complete problem. Is it okay? Are you okay with the definition of NP hard and NP complete? Everyone? Anyone has any doubt with the interpretation, any symbol or any meaning? If you're okay, then I will be giving the example. This is a bit confusing, but do not get it at all confused, no matter what is written. So NPH plus NP, don't get confused with those terms. Just understand what does it mean. Okay. So NP hard, but not say NP complete. That is a problem is not verifiable in polynomial time, is the halting problem. As we have seen, that a Turing machine, whether on having some input, whether it halts or not, that particular problem. Okay. So whether it holds on some input or not. So why it is NP hard? Already it's course 6. Okay. Why it is NP hard? Because every problem in NP reduces to it. And why not NP complete? Because it's undecidable. I've told you what undecidability is. And so it is not even in NP. And if it is not in NP, so it will not be in NP complete. Now, another one is the traveling salesman problem. So why it is NP hard? And this is the optimization version of the traveling salesman. I've told you there are two versions of a problem, either a decision version or an optimization version. Decision version has a yes, no input. Say the graphs that I was talking about, sharing with you, showing you for the TSP, I have to come back, traveling all the cities and coming back to the original source vertex. If I give you a particular solution, say I've given you the value, say 30, and I ask you that, okay, this is the optimal 2. Okay. Now, can you check that whether it is the value 30 or not? This kind of verification, or it is less than equal to 30 or not, the optimal 2 that you are getting. So it's a verification only. That is a decision version of TSP. But TSP also has an optimization version. So this is the optimization version that I am talking about. So that is TSP is NP hard optimization version. Okay. Because it's very difficult. It's a brute force, basically, as I was telling. So, and why not NP complete, the optimization version? Because it is not a yes, no type. Finding the optimal tool cannot have a yes, no answer. So it is not NP complete. Which one? The optimization version of TSP. That is not NP complete. Okay, so with that note, I want to stop here. So a lot of things had covered, and this is a bit of a lot of like missing puzzles, putting all of them together. Neither it's purely algorithm, nor it's purely automata. So it's kind of a mix of everything. So the best book that you can refer for this is Coleman. It's a one single solution. And Ahu Ullman also you can refer definitely for anything of Turing machine. So these are the two books. First, for complexity classes, there is only one solution that I want to give it to you. I hope all of you know that. That is Coleman. Okay. That's the only reference that I want to give. Is it okay? So I want to pause here. And tomorrow we will start with, yes, Coleman. Yeah, Coleman. I think C or MEN or kind of that. Okay. So tomorrow we will start with what? We will start with the smudging of the... We'll start with a very good example tomorrow. Tomorrow's class is going to be very exciting. We'll see that why actually TSP is NP hard. Where we exactly ended, we will start with that part. So show the entire state space graph kind of thing, everything. Followed by, we'll enter into the quantum complexity classes, and we will start with that why this P, NP complete and NP hard is not good enough to describe the quantum algorithms. Why we need a separate class for that. Thank you. Thank you, everyone.
Thank you, ma'am. Thank you for the wonderful session. And thank you all the participants who participated today. And one request from us, like all of you try to attend the quiz on time.